In this lesson, we are going to continue looking at the gradient of a differentiable scalar-valued function. What we will learn, or perhaps just revisit the multivariable calculus, is that if you're looking at, say, the domain of your function f here, and you're at some point, we'll call it p, the gradient gives you a sense of how to move away from p to experience certain types of change in your function. So in particular, the major conclusion that we will see is that the gradient in the domain points in the direction of greatest increase for the function. Negative the gradient points in the direction of greatest decrease. And then if you move in a way which is perpendicular to the gradient, you would experience locally zero change. So your instantaneous rate of change would be zero. So that's the major conclusion. We'll look at not just establishing that right now, but I will also give you kind of a visual example. So we'll put up a domain and sort of imagine moving around in it. And I will finish with just a brief look at the notion of gradient descent. Okay, so here are the pieces that we're going to work with. Imagine that f is a scalar-valued function of, say, n variables on some open domain A in the usual way. We are going to imagine that we are working at a point P where the function is differentiable, and let U be any unit length vector. So this is a vector in Rn, and you just think of it as indicating a sense of direction. We standardize how we give directions in mathematics by insisting that the vector is unit length. That way, it's like a rule that we all follow so that when we talk about rates of change, we're measuring with respect to the same notion of displacement. Okay, so anyway, what does it mean when a function is differentiable? Well, okay, we've talked about differentiability plenty. What I want to lift up to start this lesson is that if your function is differentiable at p, then there is a easy way to compute, say, the directional derivative of f at p in the direction of u. So this is true for differentiable functions. We can say the directional derivative of f at p in the direction in the domain indicated by u is computed by taking the dot product of the gradient of f at p and u. So that allows you to avoid, say, the limit definition of the directional derivative. So just to recap, what does this quantity represent? Well, it's like, imagine we're in the domain. So I'm just looking at, say, a picture of Rn, and I've zoomed in on some point called P. This is telling us how f would change what we would estimate as instantaneous rate of change if we were to move in the u direction in the domain. So it's like, if I'm here and I try to walk north, what kind of change would I expect for the function f? If it's something like positive 10, you would expect f to increase like tenfold relative to the size of the step that you take in the u direction. If it's 0, you would say that you don't observe at p any change in the scalar valued function f were you to move in the u direction. It's a, like all differential calculations, this is a very local instantaneous rate of change. So it's possible that you could compute that the directional derivative is 0, and yet if you were to move in the u direction, you would actually go down or up. It's just right where you are. It seems flat. Okay, so let's explore this dot product in further detail. The thing about a dot product is that we have a nice way to write it in terms of other components. So in particular, let me remind you that this dot product between two vectors can be written as their lengths multiplied times the cosine of the angle that they open up between them. So we'll say the length of the gradient. So this is a vector of numbers evaluated at p, meaning once I plug p into the gradient, it's just a vector. And then times this unit length vector times cosine of whatever angle they're opening up between them in the domain. Okay, as I was writing that, I mentioned that this is a unit length vector. So we can actually say that this dot product is the length of the gradient times cosine of the angle that the gradient is making with the unit vector u in the domain. At this moment, I want to talk a little bit more about how u must be unit length. Notice that in this computation, were we allowing ourselves to pick any kind of vector to indicate direction, we would get different numbers here. So that's what I meant when I said we standardize how we compute directional derivatives by always using unit length vectors so that we don't have any kind of factor here. Okay, there are two considerations or two cases I want to explore with this product here. The first one is that the gradient of f is actually 0 at p. So what would we conclude in that case? Well, the length would be 0. So the directional derivative in any direction indicated by u is 0. So I'll say the directional derivative of f at p in the direction of u is 0 times whatever the cosine is. And this is true for any u. While this seems like a trivial case, suppose we have a 0 gradient, bam, we will actually come back to this idea when we look at optimization. So when the gradient of f at p is the 0 vector, then we can say that instantaneously the rate of change that we would compute for f in any direction is 0. So that's going to give us a notion of flatness, for which we might imagine that f could be like bending up or bending down, because you can kind of imagine like a flat tangent plane, or analogous to Calc 1, like a flat tangent line. So this computation here, we will return to it when we motivate how we look for points where we want to optimize our function. Okay, so for our second case, just imagine that the gradient is not the 0 vector. That means that this product here could, be anything, or is anything really the right descriptor? Whatever the gradient of f at p is, it has a fixed length. So this is some fixed number. What kind of values could this cosine take? So now it's like, I want to analyze this product by thinking about cosine. Well, cosine of theta is bounded between -1 and 1, which means that regardless of which unit vector you pick, the directional derivative of f in that direction is bounded between the length of the gradient, and that's a fixed number at some point p. So this is a vector of numbers once you've plugged in p and you've computed its length. So whatever number this is, the smallest this product could be would happen when we took the gradient and multiplied it by -1, or the length of the gradient rather, times -1. And the largest it could be would be the length of the gradient times +1. So for all u, we can bound the directional derivative between two very specific numbers. So -1 times the length of the gradient is less than or equal to any directional derivative for f at p, in any sense of direction, is less than or equal to 1. Oops. 1 times the length of the gradient. So this tells us that if we are at some point p in our domain, and perhaps we've computed f of p, we want to know, if we move away from p in our domain, how would f change? Is there a way perhaps to not observe instantaneously any rate of change? Can we make it go arbitrarily steep or arbitrarily down? And the answer is that any instantaneous rate of change you compute for f in any sense of direction is bounded between these two explicit numbers. So this could be like -4 and 4. So those are the lower and upper bounds on all possible instantaneous rates of change you would see for your function in any sense of direction. I don't think that's too surprising because, again, if you're at p and f is a differentiable function, to have a nice differentiable function, you wouldn't think that from that point you could get arbitrarily steep. It's like, imagine a function turning vertical. We say it's not differentiable right there. So it's like your function can't move in an arbitrarily steep or up or down way away from p. In fact, it's constrained to live between these two numbers. So all possible directional derivatives are bounded. Let me pause for a moment, and what I would like for you to do is analyze whether or not these two bounds are ever attained. So is it possible in general to actually find a sense of direction where this would be the local rate of change, and likewise that one? I think that's pretty fast, but maybe try to write down a specific form for the unit vector that would give you this directional derivative if it exists, and likewise the unit vector that would give you that one. Let's start with the upper bound. Keep in mind that for this particular case, the gradient of f evaluated at p is not the 0 vector, so it has some positive length. If I want to achieve a cosine value of 1, that means theta, the angle between the gradient of f, which is a non-zero vector, and the unit length vector u, that angle should be 0. So u is pointing in the direction of the gradient. Let's just take the gradient and make it unit length. So this would happen if our unit length sense of direction was the gradient of f at p divided by its own magnitude. Sorry about my handwriting down there. This denominator is non-zero because we're working in case 2. Likewise, when would cosine of theta be -1? That would mean, kind of hard for my wrist to do this, but that would mean that that theta rather was pi radians or 180 degrees. So u would be exactly opposite the gradient, so just take this and negate it. So if you've computed the gradient of f at p, you have the sense of direction which would give you the greatest possible increase. It's like if you want to increase f the most, this is the way you would choose to go. Likewise, decrease if you go in the opposite sense of direction. So gradient of f points in the direction of greatest increase. Negative the gradient points in the direction of greatest decrease. What happens in between? Well, as you rotate theta from, say, pi back to 0, so if you kind of move through all possible theta values, cosine theta is going to continuously take every value between -1 and 1. So you can take your sense of direction and sort of rotate around to get every number between these two bounds. In particular, if u is perpendicular to the gradient, then we would have a directional derivative of 0. Again, that doesn't tell us that f can't change if you move in that direction, but locally we would believe ourselves to be looking at a flat journey if we were to step in the direction which is perpendicular to the gradient. Okay, I think I've said enough. So just to recap, if f is a scalar-valued function which is differentiable at p, and we want to analyze how f would change in any sense of direction in our domain, we have this very convenient way to do it with a gradient. So this is the main object of study here, is the gradient of f at p. The gradient of f at p tells us a range of values that we could use to estimate the directional derivative of f in any sense of direction, gives us the direction of greatest increase and what that increase would be, likewise greatest decrease and how much that decrease would be. We can figure out a way to go for which we would experience instantaneously no rate of change. What we are going to do next, after I step aside and let you finish writing this down, is look at evaluating such a scalar-valued function along a curve. So what would it look like if I had some space curve and I was measuring a quantity along that curve? That again will lead us to another result with a gradient, and then we will kind of do a fun exercise, a visual computation with that. What I would like for us to do now is look at one particular type of composition because it would arise all the time in physics or science. And that is, imagine that f is some scalar valued function of n variables. You could think of it like temperature, just to have a demo function. Temperature. There we go. For example, maybe f is a function of x, y, and z, like points in the room I'm in, and at every point we would associate a temperature that would be a scalar valued function of 3 variables. Then what I've written here is imagine that r is a vector valued function of scalars for some, say, interval of scalar values. It's a little bit mysterious, maybe what I'm trying to imagine here. But if r is at least continuous, in fact, we will imagine that both of these functions are differentiable. If r is at least continuous, what you're describing with this kind of construction is a curve, which we could think of in this context like a path. So this interval of scalars is like t values, time, the parameter time that you would plug in, kind of trace out some curve. So this might be r of time equals 1. This could be r of time equals 0, r of time equals 20, etc. Okay, so we have a scalar valued function of, say, 3 variables or n variables, and then we have a curve, which we want to think of like a parametrized space curve. What would it look like if we did the composition f of r of t? In words, for the context that I put up here, you could think of it as measuring the temperature as we travel along this curve. So maybe this is some very unusual looking flight trajectory. And as we trace this out, I want to compute the temperature as we do so. So that is the kind of like scientific meaning that you might encounter. And that's why I say there are real reasons to think about the composition of a scalar valued function and a curve. Not that this particular picture I just sketched would ever come up in practice. All right, so let me write out as like a map what this composition should look like. So I'm going to start with our parameter value. So you could think of this as like maybe we're looking at this piece. So the capital I interval would be from 0 to 20. I'll just say whatever the parameter values are. It's a subset of real numbers. That's our time parameter in this particular illustration. That sends us to some domain in space, in dimensional space. And that's through the action of R. Imagining that the image of R, the curve, lands inside of the domain of F, otherwise we wouldn't be doing the composition. Let's take this and plug it into F. F is scalar valued, so that actually lands us back in real numbers. So when we look at the composition F of R, we start in R and we end in R. So while R is vector valued and the domain for F is n-dimensional, if you just saw the end result of doing the composition, it would look like a scalar valued function, like the type that you might have encountered in, say, first semester calculus. And moreover, we would just say it's a scalar valued function of one variable, so let's call it t. Okay, what does it mean to take the derivative of this composition? Let me actually pause here now that I've done this map and kind of said like a word problem for what we could be assessing with this kind of computation. Do as much analysis on the derivative as you can. So what I want you to think about before I come back in just a moment is give like a story in words to what doing the derivative of this would look like. So like what does that mean to take the derivative of this composition? And again, you can think of it as temperature along this path. And then see if you can write out what the derivative would look like. Take it as far as you can. Since this composition is measuring, say, temperature, whatever the scalar measurement is along this path, if we compute the derivative of this composition with respect to time, we're looking for the rate of change of temperature at each point along this path. So in particular, if we were to compute the derivative at some point, say some time value, time equals 4 is, let's say, here, and I discovered that when time equals 4, the derivative of this composition is 0, then I would know that instantaneously at this moment, I would not observe any change in my temperature. Anytime the derivative would be positive, our temperature would be increasing along this curve. Anytime it's negative, it would be decreasing. So it's a normal derivative in that way. And it's normal in that way in that this is a map from R to R. So we take the derivative, it's kind of like doing, G prime of t or something like that. It's just going to look, if you just saw the result of the composition, it's just going to look like kind of regular calculus, single variable calculus derivative. But since this function of time is actually being given to us as the composition of, functions where the domain or codomain is higher dimensional, to compute this derivative with respect to time, what I'm going to do is use the chain rule that we've seen. So I'll say the total derivative or the Jacobian of this composition with respect to time. Through the chain rule, I'm going to write down just immediately the chain rule, kind of the most naive, apply the chain rule expression I can, and then I'll give you a better form for it. So from our previous study, I would say, okay, I'm differentiating a composition. That means it's going to be the Jacobian of the outside evaluated at the inside. So df evaluated at, any choice of point times the Jacobian matrix of the inside function. That would look like this. What are the dimensions here? Well, F is a map from Rn to R, so its Jacobian matrix will be 1 by n. R is a map from R to Rn, So its Jacobian matrix is n by 1. In fact, it's a vector. That's not surprising. As I said, ultimately, this composition is like a single variable function. So its derivative should just be a scalar. It should be 1 by 1, which it would be as a result of this matrix product. The reason why I said what I wrote down was going to be like the most naive application of the chain rule is I think that both of these components have a better name. F is scalar valued. So while df is not wrong, it's always right. So this is the correct thing to write down. There's nothing wrong with this. I just think it's hiding some of the geometry. So since f is scalar valued, what I would rather see is not this 1 by n rho. I would rather actually see the gradient of f. I'm not done writing this, but let me just highlight that all I'm doing when I pass from the Jacobian matrix to the gradient is I'm taking the transpose. I'm flipping this into an n by 1 vector. When you do that, and you think of a row times a column now as a vector times another vector, the times operation there becomes the dot product. Just like we had a moment ago, actually, when we talked about the gradient of f dot unit vectors u, same dot product. And then R is like a curve. The Jacobian vector that we're getting along this curve, that's something we normally think of as the tangent. Let's see, how would it go? Go this way. It's a tangent vector. So this r prime of t is this dr of t. So I think there's a better name for it than dr of t, and that is r prime. That really lifts up that it's a velocity vector. Okay, so if you are evaluating some kind of quantity, like temperature, along a path, something that you've parametrized, like a parametrized curve, then if you want to say, well, what is the rate of change as we move along that curve? It turns into this composition. And to compute the derivative for that, which again is just going to be a 1 by 1 scalar rate of change, we get this nice dot product form. Again, if we wanted to, we could take this dot product just like we did a minute ago and write it as the length of the gradient times the length of the velocity vector times cosine of the angle between them. We might actually take that approach in just a minute. What I'm going to do is now take this kind of understanding of viewing this vector and computing their dot product, and let's actually do a visual problem. So step aside, and then when I come back, we're going to have a picture to work with. So we'll see what that looks like. Let's work through this problem. What I've put up here, this square, is a subset of R2, the xy plane. And in particular, we're going to think of this as the domain of some scalar valued function of two variables. I'm calling it g in this problem, but it's like f a moment ago. So while this is the domain for g, what I've also superimposed on top of that is a path in R2. So you can think of the kind of pink curve, if you can see that, as the plot of some parametric curve, r of t, where this is a plane curve. Let me mention also, when you're looking at this like domain for g, these contours and this color mapping I've put up here, tells us how G behaves in the different parts of the domain. So in particular, this dark blue in the top left, that's talking about very low values of G. So that's like the low values for the scalar value function. And then as the colors get warmer until we get to, say, this bottom right corner, that's more positive or higher values of G. So this is like a contour map for this function G, kind of giving us a sense of elevation. In fact, we could say G is the elevation of, say, a mountain over this kind of flat topographic domain for the mountain, right? It's a square mountain. Just go with that. Okay. So here's where, maybe we're in a valley, and here's close to where the summit would be. And G, again, is giving us a sense of elevation as we move through this domain. Now imagine I'm a hiker, and I am not hiking on every single part of the mountain. Instead, I am following R. So it's like I have a trail, a path up this mountain, and my path is kind of meandering, but I'm starting at the slow point and I'm moving towards the summit. So what does it mean to do the composition G of R, which I'm going to name H in this problem? Well, that's like saying, what is my elevation as I move along this path? So I really just want to restrict my focus on G values along this curve. I put up here, let H be G of R, and I'm going to pause for just a moment, or I'll step aside and you can pause. And what I want you to do is analyze my elevation as I move. Sorry, I know I disappear every time I kind of go behind the square, but as I move from this starting point towards the ending point, which is over here, uh, as I move along this path, say as much as you can about h, the composition g of r, my elevation as I hike along this trail. And there are different ways that you could do this, and maybe you can try to connect the ways together. So I actually think that if you knew no mathematics whatsoever, you could solve this problem. So if I handed this to a small child, let's say, and I said, what is the hiker experiencing at, say, these four different points I've highlighted, or just in general as they move along the trail? I mean, okay, I don't know how old this child should be, but I think they could actually give me the behavior that I would like for us to also detect mathematically. So see if you can kind of throw away all the symbols and just think, what does this path tell me about what the hiker is experiencing? For that, you do need to distinguish the colors. I'm sorry if the colors are not clear. So it's dark blue is like low, then warmer you get, it's higher elevation. So what does the hiker experience along this trail, and in particular, these four moments that I've labeled? So just answer it in words, kind of qualitatively looking at this picture, and then try to connect that to the mathematical constructions that we've been looking at. So in particular, for this composition, what would be its derivative? And what could you say about the derivative at these 4 points, maybe thinking back to that dot product? Okay, so I will step aside and let you digest that. And again, my goal is that your kind of innate knowledge of how to read this map will tie to the mathematics and the gradient and this notion of how to compute this rate of change that we've been talking about. All right. I am going to start by talking through this in words, ignoring vectors and things like that. Then I will pause again in case you hadn't had a chance to think about maybe the more mathematical approach. So if I looked at this and, if you stopped me on the street and said, tell me about this hiker's journey, I would say, well, the hikers started in some valley and then they went up the mountain. At some point, like right around here, if you can see my hand behind the square, the hiker turned around. So they walked from a low elevation to a high elevation. They got up to that point, and then they turned around and they went back down the mountain for some reason. So they went down the mountain back to kind of low elevation. And then they kind of swung around and started moving towards a much higher elevation, kind of getting close to the summit. So I would say that just based on the idea of this path, R of t, going across these contours of G, keeping in mind that we're looking at a picture of G and its domain. We're looking at a picture of the domain of G. Sorry, I said that incorrectly. Okay, so that's what I think a small child could do if you kind of explain to them the context, like path went up, path went back down, path went up again. You could say, as the hiker was going up, what was the highest they got to before they turned around? What was the lowest they got to before they turned around? Start thinking about that now in terms of mathematical quantity. So when we say the highest before you turned around, the lowest before you turned around, what would we be looking to detect in some kind of mathematical equation? And then, if you've gotten through it, great. If not, here's a chance to pause again and think about now how to take this composition and keeping in mind that this is measuring my elevation along this path, look to reproduce the analysis that we just did, say at these 4 points. So kind of at near the turnaround point, the second turnaround point. Think about how working with these mathematical objects should connect to those conclusions that we just reached. Let's now do that math. Just like we discussed in detail when we were talking about temperature along that strange curve I sketched, this composition is a scalar valued function of one variable. If I'm thinking about the parameter for my path is time, so as time progresses, I'm moving along this curve, we could call the derivative of this composition h prime of t. It's just a plain old Calc 1 derivative. But using our discussion of a minute ago, I'm not going to rederive it with the chain rule, I'm just going to write it down. This h prime of t scalar quantity we can get by doing the dot product of the gradient of g at r of t and the tangent velocity vector tangent to the curve. Okay, so we don't have explicit functions to work with here, so what we're going to do is a bit of a qualitative discussion of what this dot product would return us. Anytime that the gradient of g and the velocity vector are pointing the same way, h is increasing. My elevation is increasing. Anytime the dot product is negative, I am decreasing in my elevation. Anytime the dot product is 0, I'm reaching some kind of critical point, which might be something like a local maximum or a local minimum. I'm going to add estimated vectors to this image because I don't think I can sketch on this picture and have you see it. So let me just add them with the computer. I think this vector is easier to picture right away. So my curve, we have a sense of direction because I put this arrow down here. So if I asked you to sketch tangent velocity vectors, again, this is like what we often call velocity vector for a curve or a tangent vector, you would draw them pointing along the curve in the direction of motion. So this is pretty immediate. What about the gradient of g at each point along this curve? So could you say for the 4 points A, B, C, D that I've labeled here, do you know how the gradient is pointing? And that calls back to our opening discussion, which is that the gradient points you in the direction of greatest increase. If you recall also from previous video, we know that gradients are perpendicular to level sets. Maybe I haven't specifically identified that the level sets are these kind of, or some of the level sets are these thin lines separating colors on this color map contour. Those two clues together really help you add some gradient vectors to this picture. So notably, if we're at this point A right here, the tangent velocity vector points, tangent to the curve in the direction of travel, so kind of down like that. The gradient, we want to draw it perpendicular to this level curve. So this point is kind of living on one of these black contours that we can specifically identify as a level curve or a level set in the domain of this function g. So you want to draw your gradient vector so that it's perpendicular to that level curve. Well, perpendicular could be this way or that way. Which way is it? You want to point up the mountain. So from lower elevation to steeper elevation. So the gradient of g should point kind of like this. And r prime should point a little bit like this. So I think if I do, I'm going to do it kind of off to the side, but if r prime is kind of like this and g prime, or not g prime, but the gradient of g at that point is kind of like that, they aren't collinear, but they're still pointing mostly in the same direction. So that means that this dot product is going to be positive. You can think of it as this length times cosine of an angle, which is between 0 and 90. In fact, it's relatively close. It's closer to 0 than 90. So this is going to be a positive dot product, which means that h prime at this point is positive, which is a complicated way of saying that, yep, our path is going from lower elevations to higher elevations. So our rate of change at that point is positive because we are moving up the mountain. What about what's happening right around B? Well, here, again, I'm going to do it with my hands. R prime, the tangent vector is kind of pointing that way. And the gradient of G, I'm going to draw it perpendicular to this level surface, but pointing in the direction of going up relative to the values of G. So again, it could point that way or it could point that way to be perpendicular, but it needs to point in the direction of increase so that our dot product is maybe not quite 0 right at B, but 0 right in this vicinity. We're roughly perpendicular right there, which means that right around this point, we are experiencing an h prime value, which is 0. That means that we're at, again, some kind of point where you might be experiencing an extreme value. And what's happening here, what we imagined we would be able to say if we just looked at this diagram, is that my hiker went up the mountain and then turned around right around this point. So that's like the elevation was increasing and then decreased. So we reached a local maximum right here. And we can detect that with this derivative because we know around that point the derivative would be 0. Again, maybe not right at this point, but very close to it. Same story, slightly different conclusion, but same idea up here at C. So here again, the velocity vector is kind of pointing this way. The gradient could be like that or that to be perpendicular to the level set, but it's got to point up the mountain. So again, we have a derivative kind of right at C that looks like it's the dot product of two perpendicular vectors. So again, we're getting h prime to be about 0 right here. So again, we think, hey, maybe we're reaching a critical point, and that is what happened. So as we assess, the hiker went back down the mountain, turned around, and started to hike back up. So their elevation was decreasing, and then right at C, they reached like a local minimum, and then they start increasing after that. Then at D, there's not anything too special to say at D, kind of like at A, these two vectors are pointing almost to the same direction, just slightly different. So R prime is pointing kind of this way, and gradient of g is pointing perpendicular to that level set in the direction of increase for g. That's how you know how to situate it. So we have the dot product of two vectors where the angle is relatively small. So this dot product would be positive, and we would have an increasing function that agrees with our assessment that at D, our hiker is continuing their journey up the mountain. So their elevation along this path is increasing, therefore H prime is positive. Okay, I think we're done with this exercise. So I hope this helped you tie together a lot of different notions, including going all the way back to contour maps. I love contour maps because I'm actually, maybe not so much right now, but at one point in my life, I was doing some mountaineering and I learned how to read a topographic map. I think it's always a really nice skill to have. If you haven't seen topographic maps before, you can find them on, say, hiking websites. But when you look at, say, a flat picture of a mountainous terrain and you have like elevations associated to kind of squiggly lines, that's exactly like a contour map, kind of like this one that we're looking at here, a lot more detailed than this. And if you understood, all that we were tracing out with this particular example, you might have more confidence now in reading such a topographic map. So the idea is, if you look at, let's say you're a very ambitious hiker and you have some elevation map and say these are different elevations. Oh, I don't know if you can see this pink. Pink is always a little bit light, but I've sketched here 4 elevations, imagining that I'm looking at some topographic map for a mountain. Right here, you would say the elevation is changing really rapidly. In fact, if those contours kind of collapse on each other, you could call it possibly a cliff, something that you wouldn't be able to hike up very easily. So this would be a very steep trajectory, whereas over here, it would be slow. And moreover, if you wanted to take a steep path, let's say you're a hiker on this mountain, and every time you take a step, you want to take the steepest step you can. So you want to kind of give yourself the hardest step every time you move forwards. You would, you wouldn't be computing gradients along the way, but you would step in the way that was perpendicular to your level set in the direction of increasing elevation, because this would be the direction of the gradient. And we know that that's the way you would go in order to increase your elevation instantaneously the most. That is going to lead us to our concluding exercise for this video, which is, I'm not going to go through like all of gradient descent, but I think you're at a point now where I'll just kind of outline the main principle of gradient descent. I think you'll follow it just fine. This idea of taking the hardest step to get up this mountain is what you could think of as gradient ascent. So it's like, if I want to climb this mountain, what I could do is always follow the gradient. I'm going to like go up and up and up and hopefully get to the summit of the mountain. We'll turn it around, imagine going down, down, down. And at this point, I'm almost done what I tend to do in this lesson, but I just want to, again, illustrate the principle behind gradient descent before we wrap this up. I don't have too much to say to conclude this lesson because I almost just did all of gradient descent that I wanted to talk about out loud with our previous exercise. So let me just sketch out the algorithm that I was kind of saying out loud. Imagine that we have a differentiable scalar valued function of n variables. If this is the domain, you could say n equals 2. And imagine that I want to try to detect algorithmically something like a minimum for this function. It's scalar valued, so it makes sense to think of its values as going up and going down, and maybe I'm trying to get to some kind of critical point. Well, what you could do is start with some initial guess. Let's say this point in the domain of G is a point I think might be near a minimum. Then I could compute the gradient of G. Let's say the gradient of G is this vector right here. I'm not going to write at that point, but the idea is it's the gradient at this point, so it's a specific vector. If I want to increase, I would follow that direction. If I want to decrease, and I'm going to do that because we often talk about gradient descent. If I want to decrease, what I'm going to do is flip this around, so just negate it, say in MATLAB or Python or whatever you're using, and to choose some kind of presumably small step size. So maybe my step size is only like this. Here's the whole gradient, but maybe I'm just going to take a fairly small step in the direction of negative the gradient. I'll stick with this color. Okay, so there is a new point where we can reassess. So again, let's say that the gradient of G evaluated at this point is this vector. It's pointing in a different direction than it did here, and it's also a shorter length. But what I'm going to do is say, okay, I want to go down. So let me go in the direction opposite the gradient, like that. And here I've taken relatively the same step size. What your step size should be is something that you might want to assess if you were actually writing this algorithm. And then here, my gradient is, let's say, like this. So if I want to decrease, what I could do is step like that, et cetera, et cetera. So the idea is that you start at some point, you figure out the direction of greatest decrease at that point, take a little step there, recompute the gradient, take a little step, take a little step. And what you're hoping to do with this algorithm is converge to some kind of minimum. So I don't really want to go into the details about how to pick the step and how to detect convergence, but that's the principle behind it. So we would like to descend to a minimum using the gradient. Again, you could do gradient ascent. Say I started here, I could kind of like go up by always taking a little step in the direction of the gradient. Yeah, I'll stop there. I was about to go like on some tangent about it, but I'll leave it there. And I'm going to step away right now, but what I will do is put up just a little graphic in MATLAB where I actually did gradient ascent. I don't think it's not going to be a movie, it's just going to be a picture. So you won't see the path taking shape, but you will see the result of it. So I started at some fairly low point on something which I imagine in MATLAB is like a mountainous terrain. And the path that I follow, you'll see, does take me up to basically the summit of the terrain. Okay, I hope you enjoyed this lesson. Thank you for your attention.